So we are starting chapter 2 now. The first thing that we are going to talk about is tangent lines. When you hear tangent, you probably think it's a trig function tangent. This is a slightly different application of it, but it's a very important one that we are going to focus on a lot. When we talk about a tangent line, we're talking about a line that touches the curve. Okay, so if you think about, I put on the next slide just a picture. Right here, the black here is my curve. This pink line is a tangent line. Now, the curve doesn't just have one tangent line. This is the tangent line at point P. I could do a tangent line down here. So it's just a line that touches the curve in just that spot. Now, it might intersect your curve later on, but if I were talking about a tangent line here, it wouldn't go like that. I'm not talking about a line that intersects. It is showing the shape or the direction of the curve. So it's like hitting it and bouncing off. So what would the tangent look like right here? Yeah, this curve is increasing, so the line should be increasing, and it would look roughly like that. Okay, so every point on this curve would have a different tangent line. Now, these tangent lines give us a lot of information. We will learn about what they tell us later. Right now, we need to figure out how to get these lines. So, here's my first question. I want the equation of the tangent line to the parabola y equals x squared at the point 1, 1. So we all know what a parabola looks like. So here's my curve. And we know that everywhere on this curve it would be a different tangent line, but I specifically want the equation of the line right here. Now, if you're going to write the equation of a line, what two pieces of information do you have to have? Yeah. So we need to get the slope and y-intercept, and we can get that if we just have a point and a slope. Well, I have a point, but I have to figure out what the slope of this line is. Now, slope, how many points do you need to calculate a slope? 2. I only have 1 point on that line. I don't have another one exactly. So what we are going to have to do is approximate it. We're going to have to guess at what this slope is. And to do that, we are going to make a table of values. So I did give you an empty slide after this to try to allow you plenty of space to write this out. So I am going to make a table. We're actually going to do 2 tables on this. So we'll do x, y, and then m for slope. So I only have 1 point on the line. Could you take, if I took a point on the parabola, bless you, the closer I get to this point right here, the closer the parabola is to the line itself, right? So I am going to use this parabola to try to approximate this line. So we need to start out with an x. Let's start out smaller than 1. So maybe if I start at 0. Okay, I can't get the point on the line because we don't know the line, but I can use the parabola to help me. So if I put in 0, what's the y value on the parabola? 0. How do you find slope? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So you would have to do, we're finding the slope between 0, 0, and 1, 1. All right, so if I did that, I would have 1 minus 0 over 1 minus 1, and we get the slope of 1 right there. Okay. Now, is that exact? No. What I just did is I found the slope between this point and this point. But I'm trying to find the red line. So if I wanted my line to be closer to the red line, what would I have to do? What kind of x should I pick? Yeah, something closer to 1. What's wrong with that?
How does the m, because It shouldn't be just 1 minus 0, 1 minus 0, or is that just a...
Yes, thank you. I think that's what I did, but not what I wrote. Okay, so let's get closer. So maybe a half. I'll put in 0.5. So if you put in 0.5, what's 0.5 squared? 0.25. So I want the slope, again, between this 0.11 that's on my line and this other point. So y sub 2 minus y sub 1 over x sub 2 minus x sub 1. You have that whole other slide for space. Calculate that. You can use your calculator if you need to. What do we get? Yeah, I think it's something. Make sure you do parentheses. Okay. So what that did is it found the slope of the line between this and the red one. Okay, that's closer to my red one, but still not exact. So what could I do to make it better? Get closer. So maybe I go to 0.9. So if I plug in 0.9, 0.9 squared is 0.81. So slope, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And I got 1.9. Okay, so the whole idea is I am approximating the slope of lines that are getting closer to the one I really want, closer to this red one. These slopes are all changing. I'm trying to find out what these slopes are approaching. What are those slopes getting closer to? If you just have to look at this, could you make a guess at what you think the slope is getting close to? What would you guess? 2? If you weren't sure, if it wasn't obvious, could you plug in another point right now? Yeah, we could go 0.99 if we really wanted to. So if I put in 0.99, and then when I did my slope, 1 minus 0.9801 over 1 minus 0.99. I get 1.99. Does that make you feel more confident that it's getting closer to 2? Yeah. So it looks like this is approaching 2. On homework, test quizzes, whatever, I will require you to do probably a minimum of 3 in your table. We might even, 0 is pretty far away. So you could have even started at 0.9 and put in 0.9, 0.99, 0.999. Okay, and that will give you a pretty good approximation. 1 is not enough. You can't just plug in 1 point and say, well, 1.99, that's close to 2, that's probably it. Because for all we know, if I put in the next one, it might go down to 1.98. We need several to show the pattern to see is it going up, is it going down, to make our best guess at what it's approaching. Now, we're flawed if this is what we rely on, because this only took values that were below 1. So if we want the best guess, we need to take values that are above 1 and getting close, and then make sure it's also approaching 2. So give me a number that's bigger than 1 but close to it. So we don't have to start as far away as we did to start the first time. So something bigger than 1, could we just do like 1.1? Would that work? So you plug that in. So your y is 1.21. Slope, again, we're doing slope between 1, 1 and this point. And I get 2.1. So what would be another value that's closer to 1? Yep. How about I even do 1.01? What would be one more then?
1.01.
Yeah. I like doing an easy one. So spin, and Bo, why don't you guys do 1.01, and you three do 1.001. Get your y, get your slope. You guys agree with those? So does it also look like this slope is approaching 2? Okay. So now I'm trying to write the equation. Our best guess is our slope is 2. Is that a guaranteed? No, but we think it is. So now we have a point in the slope, so we can write the equation of the tangent line. So plug into y equals mx plus b. So the y value is 1, slope is 2, x value is 1 plus b. So we get a y-intercept of -1. So my final equation then is y equals 2x minus 1. That is my best guess at the tangent line for that particular point. Question 6. So what we did right here is we were actually looking at secant lines. A secant line is a line that intersects a curve more than once. We were using all of these black lines that we were looking at. Those were secant lines because we took it from this point on the parabola to another point on the parabola. Okay, we were looking at the line between them. So we were using these secant lines to try to guess what our tangent line was. What we're actually looking at here is the concept of a limit. The slope of the tangent line is the limit of the slopes of the secant lines. When we look at what value that's approaching, that's the limit. It tells us what's happening as we get closer and closer to it, and we have to look from both directions. The way that we might see this written, we do LIM for limit, then we have underneath that as x approaches 1. Okay, of these slopes, so our slope, we are taking the point 1, 1, and then this other point, we had x, comma, how did we get the y value here? It was x squared. Okay, so the formula for your slope here was x squared minus 1 over x minus 1. So we found that and we got 2. So this is limit notation, and we will see this a lot moving forward. On the next slide, I put just a visual representation to show you what we did. We were trying to guess this pink line, so we were using these green or these blue lines here. And we just made points P and Q, 2 points on the parabola, get closer and closer to one another so that we could approximate that red line. And the closer together P and Q were, then the closer that was to the actual tangent line. All right, we can do this with actual data too, not just with an equation. So this one shows us a cardiac monitor. It's used to measure the heart rate of a patient after surgery. So it compiles the number of heartbeats after T minutes. When the data in the table is graphed, the slope gives the heart rate in beats per minute. Okay, so we're trying to estimate the heart rate here. We have a time and we have the heartbeats. So this monitor estimates that value by calculating the slope of the secant line. When you use the data to estimate the patient's heart rate after 42 minutes, using the secant line between each of these points. So let's kind of break it up. A, Corbin, B, Bell, C, Ben, D. Bo, you can also do A. So I want you to estimate, these are two T values. You're trying to find the slope of the secant line, so you're really just finding the slope. So these are like your X's. Your heartbeats are like your Y. So you have to do Y2 minus Y1 over X2 minus X1. What did you get on A?
2.
Go ahead and put. Give me a decimal on these.
69.6 repeated.
All right, 69.67. What about B?
71.75.
C. 71. Is that what you did? And what about D?
66.
Okay. So you'll notice, what do all four of these have in common? They all
42 is number.
used 42, right? If you think of it like the table, okay, my times were approaching 42. We did 36, 38, 40. The last one is 44. That's like if you had done a separate table and looked at it. So when we had 36, my slope was 69.67. When we did 38, it was 71.75. 71. 44 gave me 66. Okay, we didn't do very many above, so it's hard to tell. But we would expect the true heartbeat to be somewhere in between those two. So what's your best guess? Probably somewhere between 71 and 66. Do I have enough information to pin it down exactly? No. So we can just say, what was the question? Estimate the patient's heart rate after 42 minutes. So somewhere between 71 and 66 beats per minute. We can't tell exactly because we don't have enough information, but we can approximate it. Okay. Is that okay? I think I want to skip example 3 for now. It's the same idea, but it's a little bit uglier, and I don't want you to get hung up on the ugliness of it. I just want to work on the process instead. So let's go to this velocity problem. As we learn more about these limits, we're going to see them come up a lot. We will be using, when we do velocity, our position function. S here is representing the height at a given time. T is time. V sub 0 is initial velocity. H sub 0 is initial height. So anytime we're talking about vertical motion, this will be the equation that we go back to. You should have seen this before. We used it some in college algebra. You might have seen it in physics. does come up. The negative 4.9 is, do you guys know what that represents? It's negative if it's talking about like dropping something, it's going down. This is acceleration due to gravity. This is a little side note, that's why this works. You might also see it in 9.8 if we're in feet. 4.9 is for meters. But anyway, not an equation you have to memorize, I would give it to you, but we're going to see it. So suppose that a ball is dropped from the upper observation deck, which is 450 meters above ground. Find the velocity of the ball after 5 seconds. All right. So we could get a height equation, couldn't we? If we're looking at my height function, all right, there's a couple ways of looking at this. If you're starting out by dropping the ball, then what's your beginning velocity? 0. We're starting on top of this tower, so that's a height of 450. For the sake of our calculation, we could think of this a little bit differently. Could we say the top of that tower is like a height 0, beginning height? So, and then we could have negative heights, just meaning you're below that. Because ultimately, we don't care about the height, we're looking for the velocity, which is the speed.
These are just variables.
It's just variables. We're just going to be finding a slope, and that 450 is just going to be one more number that is subtracted off, and it's going to go away anyway. So to make life easy, we're going to assume we start at height 0, and our beginning velocity is 0, so we'll just go with this function. So if I'm trying to find my velocity, that's like speed, it's a slope, it's a rate of change. We are comparing it to 5 seconds. So if I plug 5 in here, negative 4.9 times 5 squared, we get negative 122.5. So that's like the point we're finding the slope between with all of these. And then I'm going to make you use 2 tables. One with values smaller and one with values bigger. Minimum of 3 points in each table. So it's really like my x, here's my time, my height, and slope is what we're going to find. So first, if I need things smaller than 5, so I could say like 4.9 seconds, 4.99 seconds, 4.999 seconds if I wanted. What could I use for things bigger than 5? 5.1, 5.01, 5.001. All right, so we are going to have to plug these into our equation to get the y value. So if I put in 4.9, so it'd be negative 4.9 times 4.9 squared. And then we have to find the slope between this and this point up here. Can I just put that in my calculator and not write it out? Is that okay? So y sub 2, negative 122.5, minus negative, so plus 117.649, over 5 minus 4.9. All right, so this is a little time consuming. We're going to divvy it up. Bo, you get 4.99. Ben, 4.999. Bell, 5.1. Corbin, 5.01. Logan, 5.001. Bo, what'd you get for the slope with 4.99?
620.01.
I don't know that that's correct.
Oh, that's I see what I did.
Make sure you have parentheses. So negative 122.5 minus negative, so plus 122.01049 divided by 5 minus 4.99. What'd you get for 4.999?
Negative 48.995.
Okay. What about 5.1?
Negative 49.49.
Okay. 5.01?
Did not get that far to be doing this.
Okay. Let's see. So we would have negative 122.5 minus negative, so plus 122.990 divided by 5 minus 5.01. Get negative 49. What about 5.001?
I also got
Okay, and that's due to rounding. You know, I didn't
I
keep
had
it.
much better.
Yeah, so it would. So can we tell what both of these are approaching? We're hoping they go to the same number, and what is that number? Yeah, it looks like negative 49. So the question was to find the velocity of the ball after 5 seconds. So it'd be negative 49 meters per second. At that point, after 5 seconds, it is falling at a rate of 5 meters every second. So this is an example of what's called instantaneous velocity. That is the velocity at a specific point in time. And to find that velocity, what we were doing was looking at average velocities. We were taking the slope between 2 points. So the slope between 2 points is an average velocity. In terms of tangent lines and secant lines, which one was the one where you took 2 points on the line, 2 points on the curve? Yeah. So the slope of a secant line is the average velocity when you have 2 actual points on the curve. The one we're trying to approximate is the slope of the tangent line, and that is instantaneous velocity. Okay. Do you guys want to do the last one? I'll give you class time to work tomorrow. Does that work? Do our last example? Okay. So this time I have a rock that's thrown upward with a velocity of 20 meters per second. And here is its height equation. So I want the average velocity during each time period. And I want to use that to approximate the instantaneous velocity at 1 second. Okay, you notice, what do all these have in common? Yeah, they're all starting at 1. This is not an ordered pair. This is saying from 1 to some other point in time. If you plug a 1 into this equation, what do we get out? 20 minus 16, so 4. So what we need to do is find the slope for each of these. So I'm doing it at 1.5, 1.1, 1.01, 1.001. To get the y, we plug that into our equation. So 20 times 1.5 minus 16 times 1.5 squared. So slope, we're comparing them all to this 1, 4. So y sub 2 minus y sub 1 for x sub 2 minus x sub 1. So we get negative 10 over 0.5, so negative 20 meters per second. So that's the answer to part A. On that time interval, we had an average velocity of negative 20 meters per second. So between 1 and 1.5 seconds, it fell 20 meters per second. So now we do 1.1. So plug your 1.1 in. 5 sub 2 minus 5 sub 1 over x sub 2 minus x sub 1. So I get negative 13.6 meters per second for that interval. Third one, we put in 1.01. Negative 12.16 meters per second. Finally, we put in 1.001. And then do your slope. And I get negative 12.016. So those are all the average velocities. Average velocity is just a slope between 2 points. So now the instantaneous. Can you guess what the velocity is at the point when t equals 1? What's your best guess? Negative 12. These t values, these are getting closer to 1, so as they get closer to 1, my slope is getting closer to negative 12. So I'd guess that to be negative 12 meters per second. So the assignment from this section is actually going to be a handout, not book problems. And we will have class time, maybe not a full class period tomorrow. We'll kind of see what we need.